Okay, so this is supposed to be a small introduction to Laplace and why it's useful. Um, and it's an important introduction because what I found when I was going through Laplace, there's a lot of groundwork, there's a lot of exercises, there's a lot of things that one needs to be able to do before you can see the use, why it's important, why it's useful. So the first series of these videos are just going to be looking at Laplace transforms of basic things, basic functions, and then once you've mastered the basic functions in Laplace, you then move on to theorems. There are three theorems that one needs to know. The first one is really the most important, which is the time shift. Um, uh, or really the frequency shift theorem. And then once you know those three theorems, you start to be able to do amazing things. So I just wanted to kind of give a kind of heads up for a lot of the groundwork, what it's actually going to lead to. Once you can do Laplace transforms and then inverse Laplace transforms, so it's a bit like the integration of differentiation, what inverse Laplace is to Laplace transforms. Don't worry if it doesn't make any sense, it will. But once you can do Laplace, you can start to do amazing things very easily. So one of the first things that you're going to be able to do is solve differential equations. But not just differential equations like we've solved them before, like first order and second order, but first order, second order, third order, fourth order, fifth order, sixth order, seventh order, eighth order, ninth order, if you wanted to, in an incredibly easy way. And the reason why is because what Laplace allows you to do is set up a differential equation in terms of a linear system of algebraic equations. So just like it would be, something like x squared plus 2x minus 3 equals 5, something like that. That's how you're going to be able, that's how Laplace enables you to solve differential equations. The other really amazing thing with Laplace is that you don't have to worry about any complicated methods in terms of if the differential equation is homogeneous or non-homogeneous. It makes no difference. Once you set up the initial conditions into Laplace, you don't have to worry about that. You also don't have to worry about particular solutions either. So in the classical method of solving ODE, or normal second order, first order differential equations, you have to make a guess about what the particular solution is. You have to kind of guess what the solution looks like in its general form, and then kind of substitute that back in. So Laplace says, well, you can forget all that because it just handles everything for you. So it's a much easier way of solving differential equations in first order, second order, even higher order than that. And you don't have to worry about substituting in particular solutions because that's taken into account. You don't have to guess the particular solution. So it makes solving differential equations incredibly easy. That's the magic of Laplace, and that's why it's so important. And I think it's one of the most amazing tools that I think an engineer can learn. Just for that, and obviously there's so much more. So, for instance, as one goes beyond that, you start to be able to realize that once you can set up a differential equation in a linear system, you can then solve things like simultaneous differential equations, something that we've never done before, in a very easy way. And the way is just setting it up again as a linear system of equations and solving a pair of simultaneous equations, and through that you can solve simultaneous differential equations, whether one be first order and another second order, or both second order differential equations. So that's the power that Laplace enables you to do. So I hope you enjoy the videos, and I hope they help in some way.